We're going to go ahead and get started. Thank you so much again for joining us today. And as I've mentioned before, everyone is muted for the webinar. So if you need to reach the panelists, please feel free to use chat. And if you are going to be asking questions on the content, you can use the Q&A feature in the Zoom interface. So again, there's a few little housekeeping items we're going to do before we get started. And we are actually recording everything today, and we're going to email you the slides and the recording via email, and probably in the next day or so. And again, if you have questions about the content of the webinar, please use Q&A. And if you have to, if you want to reach us directly, if you're having any issues, you can use chat. So with that, I'm going to go ahead and pass it off to Victor to introduce himself.
Thank you, Emily. So I'm Victor Lee. I'm head of product strategy and developer relations at TigerGraph. And I was to be joined today by Jonathan Herkey, our technology evangelist. Unfortunately, due to some technical difficulties, he will not be able to co-present with me. He will try to sign on and answer any questions through chat, but he's not. I'm going to be doing the actual presentation myself. So it won't be quite as good as if John were here, but we'll still try to do a credible job. So the outline for today is we're going to talk a little bit about TigerGraph's overall training and certification program, because the topic is our new certification in graph algorithms for machine learning. So I want to give you a little bit of background on what is the certification program. And then we're going to talk about our graph algorithm library on GitHub, and the previous Graph Gurus webinars, which we have available, which serve as the training content for this course. And then I'm going to give you sort of a brief overview of the content of the course, graph algorithms by category, learning to use the right tool for the right job. And then I will use the remaining time to do some hands-on examples using TigerGraph Cloud. So we set up the training and certification program to give those of you out there both some general background on what you can do with graphs and graph databases, as well as to start to learn the TigerGraph system and the GSQL language. So we have one certification called Graph Fundamentals, and it has 4 modules: Introduction to Graph Databases and Analytics, Managing Relationships. So really, now that you understand what is a graph with and why relational connections between data are so powerful, then sort of comparing that to other databases and making use of that to give you some evolution of how graph databases have progressed from the first earliest examples to the present day, and then to talk about 7 key data science capabilities of a native parallel graph database, which represents the current generation of graph databases. And by the way, you can find all of this material if you go to our website. We have this nice new website that we're proud of. If you go under the resources tab, you'll find education, training, and certification. And so what I'm doing right now is just giving you an overview of some things here. And this is the new one that we're going to be focusing on today. And also you'll see under resources webinars. And today's webinar will be added here. And a lot of our past ones, you'll see there are some which mention graph algorithms. They go through parts 1 through 5, and those are the training material for the graph algorithms for machine learning certification. So going back to here, as I said, we started off with, this is one certification which has 2 training phases, going through Graph Fundamentals and then GSQL Programming 101. And the GSQL Programming 101 has 6 modules, going from everything building a graph schema or a data model, so modeling your data as a graph, loading your data, learning to just sort of explore, inspect your data, and then writing some basic GSQL queries, a little bit more advanced queries using accumulators, and then doing real deep link queries. So it's kind of progressing from your first step to your next and third step of querying. And there's even a lot more advanced things you can learn after that. Um, and then you have certification tests, which have roughly 40 to 50 questions. And the questions are multiple choice. In this case, this is one about GSQL syntax. So it's checking to see if you can identify which one of these is the correct syntax if you want to do a basic one-hop traversal from some source vertices to some target vertices. And just pause to see if any of you already know which one is the correct one. Um, the thing to look for is that we put parentheses around the edge in the middle. So you have vertex, edge, and vertex. So checking, you can check the other little details are either the dash connectors or the directed arrow connectors, but it turns out this first one is the correct answer. And here's another more higher level command question. Do you know which is this command? And here's another one. What's the command to create an empty graph? Um, so if you want one that's truly empty, just defining the name, that would be this one, the third option. And one more question. So we don't need to go through all those questions, but so of course, if you want to, these may lead you to want to learn more. So we have documentation. You can use the free cloud platform. So we have TigerGraph Cloud is our database as a service, and we have a free tier where you can have a basic sized machine and run that for free. You can get additional community forum support, look at questions and answers that the community has posed or interactively engage with other users. And you can also go to our developer portal, which has a lot more, including the ecosystem of different resources available. I can't even go through all the things that are available here. It's constantly growing, but besides just the straight product documentation, using the cloud, TigerGraph cloud service for free, um, engaging with the community and seeing some of the resources that TigerGraph and the community have collaboratively built. There's a lot there. So spent about 6 minutes doing an intro. Let's turn to our main topic for today, graph algorithm certification. So what are algorithms? I remember I was taught as a actually high school senior. I memorized a definition of an algorithm, and this one is almost the same. It's slightly worded. It's just basic concept. So it's a finite sequence. So it's a set of steps which are well defined and could be implemented by a computer to solve a class of problems or to perform a computation. And the well defined is key. So you have a particular problem. Here is a set of steps which will give you an answer, a solution to that problem. And so the key is, there are a whole bunch, there are thousands, millions of general purpose and specific algorithms to do everyday problems and very abstract ones. But of course, we want to find ones that have some real world use. So for example, PageRank, well, Google created that 25 years ago to help them with web search. And similarity, you can find similar objects, but what type of objects are you interested in, and what type of what type of properties will you use to find out that they're similar? So those are choices that you make based on your data, but there are a whole host of issues where you might want to find similar things. It's not just matching things. Often you find one representative example. You're interested in that example, and then you want to find out if there are any others similar to that. It could be for product recommendation. It could be trying to find criminal activity. Here's an example of criminal activity where are there other cases of similar behavior or similar individuals. So there are a whole host of real world applications. So all of these algorithms are written in the GSQL language. We have an open source graph algorithm library, which are ones that we have written and tuned in the GSQL language. So it's open source. You can see this is the same language that our end users use. So you can see exactly what we're doing. So you can learn from those examples and you can modify. Most importantly, you can modify those examples to do exactly what you want. And the advantages of using GSQL, they're running on the TigerGraph platform with if it's massively parallel processing and distributed architecture, and the language naturally takes care of that parallelism. You don't have to do any low-level specification, but when it sees an accum clause, it's going to automatically execute that in parallel. Um, and do your parallel computations for you. As I said, it's the platform is scalable, and because the language is Turing complete, as we say, it means it can do anything that a computer can do. So you can express particularly algorithms. It's particularly good for algorithmic type workloads and analytical workloads. It's all in GitHub, and we have just recently modified it, the organism structure, so that you can see. Let me fix that typo right now. That obviously should say correlates with release 3.0. Actually, I can show you the graph algorithm library. So it's here on GitHub. So github.com, TigerGraph /GSQL graph algorithms. Nice README page, the open source license, the algorithms themselves, and some test data for running the algorithms. And most of the ones are schema free, which means that the particular vertex types and edge types are not built into the algorithm. These are truly generic algorithms, and that when you run them, you specify all the details about what vertices, what edges, and what attributes or properties are you interested in. So today I'm going to be able to hopefully go over about 5 different algorithms with you, actually 5 different categories of algorithms. So I'm almost finished with the presentation, and then we're going to switch to the demo. When you get TigerGraph, if you get TigerGraph Cloud, what you're going to get is a virtual machine with TigerGraph software installed on it. If you choose one of our starter kits, it will have a data model, some example data, and some queries already there. It will not have the graph algorithm library, but because the library is always changing, so we haven't yet preloaded it, but we're going to do that soon. But what you can do is we have a little widget called the algo loader that you can run, which will load these algorithms for you. And this is available on our community ecosystem. And let's see very quickly if I can find that. John has it all memorized where that is. And it is pretty easy to find, but under tools, let's see if it's a widget. There it is. It's right there. And it's actually a what do you call it? Like a notebook. You know, now see, it works with Python. Jupyter style notebooks are very popular. This is basically a simple script. So that will load your algorithm library for you. But we don't need to do that today. So I'm going to start talking a little bit more about what you'll find in the algorithm library and why algorithms are cool. And that was really something that I focused on in grad school. So this is a topic that I really enjoy. So at a high level, you can think of graph algorithms or algorithms of any sort as both tools and building blocks. So, right, as I said, we have thousands of different algorithms. They're all designed to do a different thing. And some of them have, you might think of conditions or prerequisites. They're designed to work in this circumstance. So every tool is ready to use, but you, the user, have to know when you should use that tool. So you have to sort of learn, well, under what's, in this case, what conditions, the conditions refer to your data and your graph. Do you have the right type of data that this algorithm is designed for? And then do you understand what sort of answer this algorithm is going to give? So you have a question, you become familiar with some algorithms, and you've picked the right algorithm to address the question that you have. And because real world problems are often a little more complicated, you may need to combine multiple algorithms to solve your larger problem. So once you understand, just like to build a desk as a carpenter, you're going to use more than one tool. And so it's learning to combine those tools in which sequence to do what intermediate step to achieve your final result. And that just comes from experience and applying these tools to progressively more complex problems and learning from other users in the community. So as I said, we've previously presented 5 webinars, which each covered one type of algorithm. And we started with the most basic ones, shortest path. Then we did centrality algorithms, community detection, similarity, and last ending with classification. And if you recall from the title of this today's webinar, we mentioned graph algorithms for machine learning. And the reason why we included the machine learning is because if you think about that building block phase, that when you're running machine learning, supervised machine learning, first you've got to have data, then you need features, you need training data, you may need to cleanse and enrich your data. So the algorithms are a very important step in that part of building features and cleansing data, because features are like adding dimensions to your data. And graphs give you unique features which you would not have if you were only looking at your data tabularly. Each of these algorithms generates a result, and those results can be a feature. And those are things which, we can talk about the use cases, for example, why shortest path might be an interesting feature for some, understanding, again, trying to understand, is this a good prospect for marketing? Is this a fraudulent user? Understanding who are they connected to? How centrally are they located in the community? Are they within a community of known fraudsters or known influencers, things like that. So these can be very valuable. This last step, classification, actually is a form of machine learning. And we talk about using one of our algorithms, the k nearest neighbor, which really is a machine learning algorithm, and how that applies to graphs and graph algorithms. So I can say a little bit more about these different cases. I'm not going to go too deeply because I want to show you. But again, sort of top down from the most basic to the most sophisticated, I think let's look at the use cases. Search is really, it's really understanding just how do you want to move through a graph. And for the most efficiency, you want to use the breadth first approach for almost all of these. So almost all of these just build on breadth first search. It's not an algorithm by itself, it's just a way of working. Pathfinding, maybe you want to find the shortest route because you're doing physical transportation or communication, or you're trying to just make sure you span or cover a region efficiently. You're trying to optimize a process. What's the most efficient way to get through all the steps necessary to build something? Centrality or ranking. PageRank is a form of centrality, understanding what's the influence of a particular node. But there are other forms of centrality, closeness centrality and betweenness centrality, which traditionally were defined for physical locations. What's the most centrally located thing, which might be good for, again, transit optimization, um, clustering, or finding the natural groups. There's so many uses where finding the natural groupings based on what is their connection pattern. So here we're using the interconnection pattern to define what is a group. Are you connected at all? And how densely are you connected? And so does that represent similarity? Does it represent communication between those individuals? And again, it could, depending on the type of graph, this might be useful for science, it might be used for marketing, for your operational activity, all sorts of things where understanding how things naturally group, um, knowing that consciously and being aware of that gives you a lot of power. Similarity, as I talked about, recommendation, and don't think just about retail recommendation. Think about advice. Just knowing what things are similar gives you advice, gives you, ah, that's something I should, if I know this, I know these other things are similar. And lastly, we talked about classification. You have a bunch of examples of something you want to know. This time, it's not doing grouping like we did in here. We were doing grouping based on their interconnection. This is doing grouping based on having similar characteristics. So it's leveraging actually the previous case. So again, these were arranged in a certain logical order, so they tend to build on one another. There are other ways to classify algorithms and which you will find useful. Again, I mentioned knowing what type of graph is appropriate for this algorithm. And the key characteristics are your connections directional or undirected? And do those connections have characteristic strengths or weights? You also, is the algorithm a global one where it examines the full graph, like PageRank, or is it local, only exploring as far as it needs to from a starting point? What type of output does it produce? Does it give you one number, or does it give you a score for every vertex? That all of these have a big impact on the computational complexity. How long will it take to run this algorithm? TigerGraph is the highest performance platform in a lot of cases, but it's limited by the the inherent logic and physics. It's always going to take longer to do a million steps than to do 1,000 steps. Um, and so some algorithms, as we will see, just take longer than others. So I'm going to spend maybe 5 minutes again going over some examples on slides, and then we're going to turn to Graph Studio and TigerGraph Cloud and run them for real. So, so shortest path. The example I used here is airline routes. That was the example I used when I was planning this about a year ago. Airline travel is starting to pick up again, but let's do truck routing. It's equivalent. So how do you get from city A to city B? If you only care about how many stops you make and you don't care about the distance, then that would be what we call unweighted paths for shortest path. If you do care about the distance traveled or the time, then that's a weighted shortest path. And so you can see you could get different answers where if you just count the number of hops, this blue one takes only 3 hops. So that's a shortest unweighted path. But if these numbers represent time or distance, then taking this detour to D is actually shorter. So then going A, D, C, F, H would actually be a shorter path if you care about weights. Centrality, as I said, if you wanted to find where's the best place to put a warehouse or a distribution center if you need to deliver to all of these possible destinations. And closeness centrality will tell you is one way of measuring which one has the shortest average distance to all the possible destinations. Betweenness centrality is slightly different. It assumes you're going to be going from place to place, and which one sits along the most paths. And I give the example, where would you want to put a coffee shop or a gas station? Because people may not be thinking of it as their destination, or like a fast food restaurant. It's not necessarily their destination, but if you happen to be along their route, they're likely to stop there. I mentioned PageRank is also a form of centrality, and PageRank measures influence in a certain way. So if we give a use case of example of medical practitioners who make recommendations to each other, and you're trying to find who is receiving the most recommendations, like who is considered the best expert. So from one doctor to another doctor, so maybe this Dr. Thomas is the most influential doctor, and which we find out from PageRank. And then we do a follow-up computation about community to see who is he tightly connected to, and finding out, well, who does he influence? So there's sort of two questions. Who's the most influential provider, and who is he influencing? Lastly, we're getting close to the end of this. Talk about similarity cases. This is another healthcare example. This represents the large graphic here. The table is a timeline showing the different interactions that this patient or member has had with the medical services facilities and community. And there are a couple activities that are flagged. And so this is an interesting case because of these flags, these alerts. And we want to find out, are there similar members who also we want to know about, who've also have seen gone through a similar patient journey. And by at the application level, you just click this button to find out what other similar users are. Under the hood, this is running a similarity algorithm. And I think I'm going to kind of skip over this. I'll just very quickly to say, you can think of it, if it's modeled this way, this is an individual, and each of these connections is a connection to a characteristic or property. What you're asking is who connects to similar things. And so this is how you formulate it as a graph problem. And what our users have found out, that doing it with a graph database like TigerGraph is actually more performant than trying to do it in a traditional tabular way. So it's finding who has the most similar connections. A and B both connect to X and Y, which is 2/3 of their overall connections. I'm going to skip this one. And I see I had a question about how does this relate to classification? Once you understand the characteristics of a person of interest, like that patient with the alerts on their journey, there may be other ways that you've characterized and labeled different types of people. For a fraud detection system, you may have determined these 4 different types of users. And then you want to say, well, now I have some data. I don't know what the label is. I know their characteristics, but I don't know how to classify it. So this, again, if you have a graph-based similarity model like this, then you have you use that graph-based similarity to then help you with your classification problem. And with k nearest neighbor, you're using we're measuring similarity as a distance, and that's what we mean by nearest. And again, if that similarity is a graph type similarity, then it becomes a graph problem. So I've got about 25 minutes left to do the demo. I'm going to jump right now to TigerGraph Cloud. I see here's my home dashboard. Sees the different, each of these are different instances. I could, if I wanted to create a new one, I could click create new. We have about 7 different categories of starter kits, like graph algorithm. I started with this one, graph algorithm centrality, and then I enhanced it a bit. The notes, my slides here show you how I enhanced it. That's actually downloadable, something you can download. And then I would select, the default is we can run on AWS or Azure. You can run a free instance on AWS, and or you could choose a larger paid one, and then you can also select what region you want to run in. Um, you name it, and then you click create next, and it'll just create it. I don't want to do that. I already have one, and it's actually already here. So my data set is this airport network. I have this is public data that I got from the internet. So it represents just about every commercial airport in the US, excuse me, in the world. I believe there are 8 or 9,000. We'll see on the next page. And then I have 3 types of edges. And notice they all loop back to airport. There's only one vertex type. It has ID, name, city, country, IATA code, like SFO for San Francisco is the IATA code, latitude, longitude, score, and community ID. Um, there is an undirected edge called flight route connecting one airport to another and how many miles are between airports, and what airline flies that route. And there is the same information but directed. So I actually would recorded the same information to say either you can get between San Francisco and Chicago, but I'm not telling you in what direction it goes. And then this one is actually directed. So it goes from San Francisco to Chicago. And then we are going to enrich the data later by adding similarity. The original data doesn't have similarity data between airports, but we can add that. This is showing how we load our data. So there's a CSV file which contains the information about flight routes and airports. And I already loaded the data, and I said there are about 8,000 airports, about 38,000 directed edges, and currently no similarity edges. Oh, I want to show you one thing. I want to show you something also about the airport IDs. So, and how I want to explain how I labeled the airports. In the original data set, not every airport has an IATA code. Some are smaller airports. The data set had its own just numeric IDs, but those didn't have any real world meaning. So what I did was I constructed IDs by combining the IATA code when it's available with the numeric ID. So there's always something there, but I wanted to use the IATA code when it's available. So what I'm doing here is I'm searching for the full ID of the airport that's closest to me. The airport that's closest to me is Canton Akron with CAK. And so that's the full ID, CAK-41112, because I'm going to be using that later. And so let's start off. Let's do shortest path, no wait. So shortest path, no wait. So again, this is just how many hops it is. And this is global. This is doing it for, oh, it does say single source. Well, it's doing from Canton Akron and asks you, okay, what sort of vertex type do you want, airports, and what sort of edge type do you want? Let's do flight directed. So we should do flight 2. And that's all we need to specify. And it's done. And what's this telling us? Okay, it means I can get in 4 hops from Canton, Akron, through Detroit, through not even sure what PVG is. I can do the ZQZ. Unfortunately, I don't know what airport that is. If you scroll down to the bottom, see it did 45,000 lines of information very, very quickly in a fraction of a second. I know there is one here. Ooh, 7 hops. There's a short one here that I actually recognize. You can see Atlanta and Dusseldorf or Narita. There was one that was only 2 hops. I think it was getting to Frankfurt. I think you can get from Frankfurt in 2 hops. It goes through, see if we can find it in about 1 second, or I'll give up. Don't- Yeah, there's so many lines. Anyway, it's probably not worth it. But that's unweighted shortest path. So let's do weighted shortest path. And before I do that, I actually need to add the mileage. The original data did not tell us how many miles it was from one airport to another. So we wrote a very simple query, which takes latitude and longitude for 2 airports and calculates the miles. And so I want to add it on the flight 2 edges. And it's done. And also for the undirected flight route edges. And it's done. So now I have mileage between airports, and I'll run it for shortest path with where miles matter. And again, from Canton, Akron. Oh, sorry, did I skip airport? Type airport. The edge type is flight 2, and now I have to say what is the name of the attribute with the weights. It happens to be called miles. If you look here in the schema, flight, it's called miles, and it's an integer. So we say int, and now we can run. Now this will take a little longer. Logically, we're using more complex information. We're now using numerical distance, not only because it's using numbers, but because of that, you actually need to explore the full graph before you can even come up with a single answer. Like, just because I find a route from Akron to San Francisco, it doesn't mean it's the best route. And you might be able to come up with some real world shortcut. You say, well, there's no way it's more than 4 hops. But the algorithm doesn't know that. The algorithm is exploring the entire graph to find even one answer. The good thing is it can actually find every answer from Canton, Akron to every other airport with the same amount of work. So at least you get that. It turns out I enhanced this one slightly so that it also prints out the names of the city. So it's a little more user-friendly now. So we're finding all sorts of bizarre connections, like how to get from Canton, Akron to Jiayuguan, somewhere in China, Nanyang. So all sorts of places you might not even realize you wanted to go. Let's keep moving. PageRank. PageRank, it turns out, is actually a very fast algorithm. And let's run it and then talk about what it means. Because each of these is going to give slightly different answers. And again, I said, it's talk about learning to understand your tools and learning to interpret the meaning of this result. This is going to give us how many top K. It's going to give us the top 100. I think they're sorted. Yeah, and I said it's very fast. Atlanta. PageRank traditionally uses directed edges pointed inward. A entity will have a higher rank if it has more edges pointed to it, and if those incoming edges are coming from vertices that they themselves have high rank. So your rank depends on the rank of your in neighbors and how many in neighbors. So Atlanta, that means it's the highest page ranked airport, meaning it has incoming flights from a lot of airports and a lot of important airports where they themselves are these sort of in hubs. Next is Istanbul, then Chicago or O'Hare, Denver, Dallas, Fort Worth. This turns out this is in Moscow. I had to look that up. This is Charles de Gaulle in Paris, Frankfurt. All major world cities, all major airline hubs, makes a lot of sense. Let's run a different type of centrality, closeness centrality. And again, we need to know what vertex type, what edge type. That was flight. I think we can use undirected for this. So I'll use flight route. And I think I can accept all the defaults for this. Now, closeness centrality is now calculating all shortest paths from to or from my, did I specify a hub? I didn't. No. So again, this has more work. This is actually a slower algorithm than PageRank because it has to do more work. But now the answer is Frankfurt, Charles de Gaulle, London Heathrow, Amsterdam. I forget where DXB is, but then Los Angeles, New York JFK, Toronto. The idea here for closeness centrality is if you want to start from here and then fly to any other airport in the world, where is the best place to start from so that you have to make the fewest connections? In other words, it's sort of the average shortest path to all possible destinations. Now, this is a little bit not quite so realistic because not every airport in the world is of interest to you. You're probably only interested in certain destinations, whereas this considered every destination. So the straight algorithm as is might not be what you want. And that's why the ability to actually edit and modify these algorithms is very useful. So let's do one more. This is betweenness centrality, and we'll run it. And while it's running, again, we'll talk about what it means. Flight 2, yeah, sure. Let's see. Now this one is going to, is it asked for an attribute? I don't see where it's asking for an attribute. Again, this is where I said it's like the gas station or fast food restaurant location analogy. The situation is it's computing shortest paths between every possible pair of vertices. So in the global community, if people are trying to get from here to there, from every possible here to every possible there, which other vertex is on the most, sits along the most routes? Which one is going to get the most pass by traffic? And in the airport domain, this is thinking about if you're trying to get from here to there. Again, if I'm trying to get from Akron, Canton to San Francisco or Beijing or Frankfurt, which airport am I most likely to connect through? So this is one of the most popular connection airports in the world. LAX, Charles de Gaulle, Paris. I think this is actually Anchorage in Alaska, which is interesting. I forgot what DXB is. Frankfurt, Peking, Chicago, O'Hare, Amsterdam, Seattle, Tacoma, Istanbul. So a different set of answers, not the same as PageRank, not the same as closeness centrality, but you can also see the logic there. That's two categories. We've done shortest path, we've done centrality. Let's do a community detection quickly, and then we'll wrap up with similarity. Actually, I'm going to do similarity first because it's a little easier to do, and then the community detection takes a little bit more explanation of what we're doing. Jacquard neighborhood similarity. So in this case, I need to give a starting point. So I'm going to give Canton, Akron. And what we're doing is saying who has a similar, what is a similar airport? In this case, it wants to know both a directed edge and the name of the reverse directed edge. Graph Studio and TigerGraph Cloud automatically name, if you choose to have reverse edges, it automatically uses this prefix reverse underscore. I think we only need like 10. We don't need 100. And let's print it out this way. And so Rochester in New York, Greensboro in North Carolina, Savannah, Georgia, Syracuse, New York, Dayton, Ohio. These are all in the eastern US, like Canton, Akron. They're all what you might say are sort of second tier cities. They're not hub airports. They're not major cities. They're notable cities, but you would fly from here to one of the hubs. And so that makes sense why this came up with these all have high Jacquard similarity scores. They all connect to the same airports that Canton Akron connects to because they're in the eastern US. They're not hubs, but they're connecting to hubs. And the last one I'm going to do is a community detection. And we're going to run the Louvain algorithm. Louvain measures modularity, and modularity is a sophisticated way of measuring community. What it looks at is what is if you look at the connection degree of a vertex, the degree is the number of connections it has. And then if you look at how many of those connections on average go to other members of the same community versus connecting out of community, if you just sort of randomize the connections. So looking at the actual structure versus what would the structure be if we kind of randomized it. And you can come up with a score saying how much better is the actual. If you have to first, you make a proposition, you make say, let's say these are my communities. So now I have some hypothetical communities, and you can score that. You can say, I've got these many in-group connections versus how many I would have if I just randomized them. And what it does is it progressively tries to find better and better community groupings so it maximizes that modularity score. And Louvain is a particular way of efficiently doing this. It's perhaps the most efficient way known. So again, airport is my vertex type. My edge type is flight 2. And weight, now it uses weighted edges, so we use miles. Double check something that is, yeah, it's designed to use integers. I don't think I need to set anything else. And this warning says the graph size exceeds the limitation. The graph will not be rendered. So that's just saying that it's not going to visually draw the graph. The algorithm ran fine. It's just a very technical way of saying the graph is too big to draw. But we get the numerical results. And I'm going to scroll down to the bottom. And this requires a little bit of explanation. If you remember, there were about 9,000 airports. What this is saying that 4,883 of the airports fit into one community, and this is the ID number for that community. That is not a size, that is just a random number for the ID of that community. The next largest community, so realize this is like 60% of the airports. We make a huge jump down to only about 6% of the airports fit into this ID. And then when we get progressively smaller, as actually I'm going backwards, and suddenly we jumped all the way down to, there are only about 7 airports that have more than 100. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There's that one community with almost 5,000. There are about 10 more that have over 100. And now we're down to 67. And what I'm going to do is, okay, this is a small enough number that I can remember that 232. What I'm going to do is go over to Explore Graph. And I'm going to modify this property filter so that it's looking for the community. Oh, you know what? I need to rerun this algorithm. So the thing is, I want it to save these values. Let's see, where am I? Yeah. I need to rerun this algorithm, and I need to set this property, the result attribute. I need it to save the results on the community ID attribute so that I can then search for it. So I'm going to search the community ID, and oh, I forgot what value I was looking for. Was it 282? Further down. There's an interesting 231. It's about 100. 232 has 34 airports. And set this to 232. Actually make this an integer, and 232, right? And so you see all the airport codes, but I want to also display the names of the cities. I think that will help. Okay. Wow. Let's just to be a little clear, I think I know where these are, but yep, they are in the US. And you're wondering, whoa, those don't sound like US cities. What you might realize, they're actually in Alaska. And so what we found, this is not the community I was expecting. That's okay, because I don't have this totally pre-planned. I am acting like a data scientist and it's just exploring. These are all in Alaska. And what this is saying is these are not tightly connected to some of the more global. You're not going to get here flying United or Delta or American. You're going to have to fly a smaller regional airline that connects these cities. And that's why these got grouped together. And again, it wasn't looking at their geographic location. It was looking at their pattern of interconnection. So I think I've timed it about right. Go back to my presentation. So I went through 4 different types of algorithms. These various cases. We did pathfinding, centrality and ranking, community detection, and similarity. I said, if you want to know more about these, you can, I would go to TigerGraph's certification page. You can see the webinars that go into these in depth. They all have running examples that you, again, I did a quick summary of the examples. All of them have working examples you can run. If you just go through the presentation phase and tip, when you start to go through the second and third, you can kind of skip over some of the intro because they are reviewing. So it won't take you an hour to go through each one. It's very relevant. We've had a number of people recently take the graph algorithm certification test and get only one question wrong. And we went back and looked, oh, we actually had the wrong answer. So we had a number of people get perfect scores. At the same time, I was told I wrote the test and people told me it was kind of hard, but people were also getting perfect scores. So we're hoping that you go out there and try it, and happy to answer your questions.
There's a few questions there for you.
Yeah, let me see. So
Jonathan's on, but I don't think he has his computer. He's just on audio.
Yeah. So I'll just start from the top. I think I saw the first question about why KNN relates to graph. And it has to do with, well, KNN uses similarity and distance, and we provide some examples of where you might be using a graph algorithm for similarity and distance. So it's not inherently graph, but it fits in with your graph realm. The second question, can you say a little bit more about pattern detection and recognition in a graph? So yeah, I'd love to do that. So in the graph query language, there's actually built-in capability for a pattern. And I'm not sure if any of these, so the thing about algorithms, there's a difference between generic pattern matching and classical graph algorithms. Classical graph algorithms um, do solve very fundamental problems, which can be expressed in a very generic way, and they tend to be step by step, which means that they're only looking at one graph hop at a time, which by definition is not really a pattern. It's only when things come together that it becomes a pattern. So for example, PageRank, it's only traversing one hop, and it's any hop. So there's not much of a pattern there. The pattern comes out in the answer, not in how you pose the question. The question is very generic, but you could certainly write a more complex expression here. We support multi-hop traversals, and where you can specify exactly what type of vertex and what type of edge. So if you can describe your pattern as a path of particular features. I want to go from, from a person to knows another person who bought a product and used a certain type of, used a computer to purchase that product. If you can express what you're looking for as a chain like that, you can do it as a query. There are also generic algorithms for pattern recognition, more broadly, what we call graphlets, and they typically work by finding the smallest possible patterns and then seeing which ones are frequent, and then trying to build them, connect them, say, well, I see pattern little two vertex pattern A occurs a lot, two vertex pattern B occurs a lot. Do pattern A and B ever intersect, making a three vertex? I now made a larger pattern by attaching these two. And so there are algorithms that do that. They tend to be computationally expensive. So we don't have those as a generic algorithm, but those certainly we can help you do that if that's what you're interested in doing. See, what virtual memory size am I doing? Because I'm doing this webinar and I wanted to go slightly, I didn't want to have you guys waiting. I did bump up and used the smallest of the paid machines. So when I created the new instance, instead of taking the free one, I used this one. Now, I gave this same webinar during our recent Graph Plus AI World, excuse me, Graph Plus AI World conference. That was pre-recorded, and I was sort of able to edit out some of the wait time. Let me show you something. The run button has a little option here for run configuration, and you can set either the default runtime, which is 15 or 16 seconds, a default timeout. Yeah, the default is it will time out after 16 seconds. All of the examples I showed you, you can run on the free machine and they'll finish in under a minute. But a minute is longer than 16 seconds. So I could have just changed this, but I also didn't want you guys to have to wait for a minute. So I chose to bump up to one size up. Those are all the other questions. I want to see if anybody has any more questions. You've got a couple, you've got a minute to, text me a quick question. But I hope this has been informative. I don't know if it's been the most coherent, but at least this is a topic that's really interesting to me because I said I did this and I was interested enough that I wanted to do this stuff in grad school. And then I got lucky enough to find a job where I get paid to do this type of stuff. So thank you for joining us. I do have a couple wrap-up thing to tell you. We'd love to have you join our next webinar. It's actually going to be a 2-hour workshop, which is a week and a day from now, or a week and 2 days, for Graph Guru workshop on no-code graph analytics by one of my colleagues, Emma Liu, and some of our engineers. And we're going to show you the capability in TigerGraph 3.0 to both build queries and to ingest, migrate data from a relational database just through a UI without writing any code. So that should be really exciting. Sorry,
There's,
John, go ahead.
there's 2 more questions.
Oh, let's see. Yep, this was all single machine. If I were to run, one of our benchmark tests, so if I had 4 times as much data and I had 4 machines running in parallel, the page rank would have completed in approximately the same time. Or actually, if I took the same data and spread it across 4 machines, it would have finished almost 4 times faster. So that's the power of some of these, and it depends on the algorithm, which again, whether it's global or local. Is there any way to do an ad hoc query that isn't transformed into a precompiled inquiry? Yes, we have interpreted mode where you can just write it out. You don't have to compile it. You can just write it, and I can in 5 seconds show you if before these are compiled, if you can just click this run button even before it's compiled, and it'll just run in interpreted mode. So thank you, and we'll see you next time. And again, hope to see you at our next workshop. And you can contact me at victor@tigergraph.com.
Okay, thanks, Victor.